Crazy Hat Chemist, so another video here on Thermodynamics 2. So let's get moving. Bam! So today we are talking about Gibbs Free Energy calculation number 5. Count up number 5, baby. Here we go. Alright, we're going to determine the delta G naught for the dissolution of ammonium chloride in water. Given the following thermodynamic values at 25 degrees Celsius, that's 298 Kelvin. Now, first of all, you need to know the formula for ammonium chloride. So, ammonium ion is a polyatomic ion of a 1+ charge. Chloride is a halide or a halogen ion of a -1 charge. And you're going to put those two things together and you're going to get NH4Cl. That is an ionic compound because it is composed of a cation and an anion. It's a polyatomic cation and the anion. Okay, now it's the dissolution of this salt, an ionic compound, in water. Okay, so think about it here. We're going to put this salt in water. You're going to stir it around and then whew, it looks like it disappears. But really what's happening is you are breaking up hydrogen bonds in water and you're disassociating the cation from the anion of the ammonium chloride, which is the salt, because the polar water molecule is ripping away and hydrating the chloride and the ammonium ions respectively. So you should actually have a good idea of what's happening with this reaction. You should be able to write the balanced equation. It's super simple here. Okay, and you should be able to look in the back of your textbook and find those thermodynamic values that we're going to be using here. That is some appendix in the back of your textbook, and find those and look up ammonium chloride in two different states. One is the solid state, one is in the aqueous state, that is in water. Okay? Alright, so here are those thermodynamic values. We got ammonium chloride solid and ammonium chloride aqueous. Okay, and we have S naught values, we have delta H values, we have delta G values. We have values for all of these. There are no elements in their standard state. This is a compound, ammonium chloride, so therefore you wouldn't expect any of these values to be 0, as you see in these values here. Okay, make sure that you do pay attention to the units for each of these, whereas the entropy term is a whole separate set of units, and the enthalpy and the Gibbs Free Energy are very similar, if not the same, as far as the units. Okay, so now we need to write that equation. So here's that equation, and I already let you know what it should look like, but it's a NH4Cl, that's solid. That's before you place it in the water, excuse me. And the ammonium chloride in the aqueous state. It's a 1-to-1 ratio. I don't need to write water on either the reactant or the product side. By having aqueous on the product side, that indicates that this is in water. All right. Now, there are two methods or two different processes of solving this problem, giving that thermodynamic values here from the back of your textbook. Okay, just like on the previous Gibbs Free Energy calculation number 4, this is very similar. Okay, so the first way of doing this is delta G naught is equal to the sum of the delta G naught of the products minus the sum of the delta G naught for the reactants. We only have one reactant, we have one product. This is super simple. This is NPR. Okay, naught, that is the 0, at standard state conditions, products minus reactants. This is the second method. The second method is first determining the enthalpy for the reaction, then the entropy change for the reaction. Using those two pieces of data, we're going to plug that into this delta G naught equals delta H minus T delta S. So we're going to do both of these, and then we're going to analyze the data to figure out what this means. Okay, so, excuse me. The delta G is equal to 1 mole of the ammonium chloride times the value here for it in the aqueous state. Remember, it's products minus reactants, minus the 1 mole of ammonium chloride times its value in the solid state. I'm going to get a value for this, and that's -7.49 kilojoules. Okay, that negative sign should let you know if this is spontaneous or non-spontaneous. I'll touch upon that in just a moment, but you should be thinking about that. Then we're going to get the enthalpy term for this, and it's 1 mole of ammonium chloride times the value in the aqueous state minus 1 mole of ammonium chloride times its value in the solid state. And we're going to get a value for this. This is 14.89 kilojoules. And looking at the sign of this value, you should also understand what this is, either indo or exothermic. And I'm going to come back to that in just a moment, but I'm giving you time to think about it. Then we have the delta S, or the change in entropy term. And that's 1 mole of the ammonium chloride times its value in the aqueous state minus 1 mole of ammonium chloride times its value in the solid state. And that's going to be a value here of 75.1 joules per Kelvin. Again, this value is positive, so that should let you know what this should be at. Is this ordered or disordered? Okay? All right, now we do, in order to plug this into the delta G, not for the reaction, we need to actually change the units on this, and that's what we're going to do right here. It's still a positive value, so the sign has not changed one bit at all. Okay, now we have this in kilojoules per Kelvin. Okay, and now we're going to plug both of the enthalpy and the entropy term, as well as the temperature at 25 degrees Celsius, converting it to Kelvin into that Gibbs free energy calculation. And that's what we've got right here. And now I've got a value for that, and that is negative 7.49 kilojoules. You should see that both of these values are the same. You should be able to get the same value, if not very, very close to it, just like on the previous calculation, number 4, the previous lecture. Okay, now one thing what we need to do now is analyze the signs of these numbers and ask ourselves, what do the signs of these numbers mean? Okay, so given that the Gibbs free energy sign is negative, okay, again, it doesn't matter which method you use, because Gibbs free energy is negative, that lets us know that this is a spontaneous reaction. All salts dissociate when placed in water. That totally makes sense. Try this at home. You could take a cup of water and then add some sodium chloride, that's table salt there, swirl it around, and it looks like the sodium chloride disappears, but it actually dissociates into the water. It does not dissolve. Okay? Sugars, molecules dissolve, but ionic compounds dissociate. So we do know that this is a spontaneous reaction because Gibbs free energy is negative. Now, the enthalpy term, the delta H term, is positive. That lets us know that this is an endothermic reaction. So if you were to do this at home with ammonium chloride, you should be able to put a thermometer in a cup of water, add some ammonium chloride to it, swirl it around, and you should notice that there is a temperature decrease. This is an endothermic reaction, that is reactant favored on that one. Okay, and then we should see that the entropy term, that is the delta S term, is positive. Okay, and this positive entropy term is letting you know that it is more disordered. Okay, and that is that the salt, ammonium chloride, was originally in its ionic state of very ordered. The water molecules were very ordered, and then that salt dissociated, which became more disordered. You're breaking up hydrogen bonds. Okay, so that is a product favored process. And you should see that the enthalpy delta H and the entropy delta S are of the same sign. And when they are of the same sign, I do not know the sign of Gibbs free energy unless I do the calculation, which of course we have done right here. So after having done the calculation, you should know what's the driving force. Again, the enthalpy term of delta H is positive and endothermic, that's reactant favored. Okay, and the entropy term is more disordered because it's positive, and that's product favored. Comparing those two, the Gibbs free energy is negative and product favored, and therefore spontaneous. And what is product favored as well? It is the entropy term. So this reaction is spontaneous and driven by the fact of entropy. Okay, because the entropy is positive, it's becoming more disordered, which counters the enthalpy term, which is reactant favored and endothermic. Okay, this should make sense because the higher entropy in the disruption of the hydrogen bonds as well as the crystalline structure of the ionic compound in breaking up that salt occurs. Okay, hopefully you enjoyed that. That was a great video here. I don't know. I thought it was cool. Give me a thumbs up. And of course, subscribe to my YouTube channel. And we can't end this chapter or this lecture without a crazy hat. And so, therefore, a crazy hat. I believe these hats are from World War I, so not that my dad is this old, but thank you very much, Dad and Paula, for this hat specifically. So, don't forget, you can find me up on, find my website, and you can get a sticker or maybe even a t-shirt, okay? There is my website right there. You can't miss that. That's my website. Okay, my son made this sticker and that design. I love it. It's super cool. Okay, I hope you have a fantastic day. We got a few more chemistry videos until this unit is finished. So I will see you next time. Bye for now.